Hi guys, happy Tuesday. We are talking about percent yield and multi-step reactions today. So percent yield is this idea that whenever we do a reaction, it's pretty rare that we get all of the product that we're expecting out. And so it always reminds me of the saying, 60% of the time it works every time. So a little analogy to think about this is that my favorite pancake recipe, gluten-free pancakes of course, makes 8 pancakes, or so it claims. But often I'll put in all the ingredients the way it says for 8 pancakes, but I might only get 5 off the griddle. So what happened to my other 3 pancakes? Admittedly, I make giant pancakes, so that's probably the actual problem, but you get the idea. Sometimes we expect to get a certain amount of stuff out of a recipe or a reaction, but we actually get less than what we were expecting based on what we put in. And this is the idea behind percent yield. And percent yield is really important when you're considering how successful a chemical reaction is. A lot of chemistry is trying to figure out how to make the thing you want from some stuff you don't want. And so in addition to figuring out if you actually made what you were trying to make, you want to know if you made a lot of it or if you only made a little. My experience in organic chemistry lab tells me that most of the time you only make a little and it's probably not even what you think it is and you should just give up and cry. But that's just because I was bad at organic chemistry. Okay, so theoretical yield is something that you guys have been calculating for a couple weeks now. When we use stoichiometry to find how much product can be made by the reactants, we're finding the theoretical yield of the reactants. Theoretical yield is the amount of product the reaction should make based on the amount of reactants. We can find this using stoich. So for example, if we have this little reaction shown in the bottom right, this is methane reacting with oxygen to make carbon dioxide and water. So if I react 5 grams of methane with 20 grams of oxygen, I can figure out what the limiting reactant is, and then I can calculate using stoich that I should get 13.7 grams of carbon dioxide and 11.23 grams of water. I don't know why it says plural waters, but that's cool. Yeah, so we can confidently say when we're doing this reaction, this is how much product we're expecting to get out. The actual yield is how much stuff we actually get out of the reaction. So in this case, when we reacted our 5 grams of methane with our 20 grams of oxygen, we were expecting 13.7 grams of carbon dioxide and 11 grams of water, but actually we only made 10.28 grams of carbon dioxide and 8.42 grams of water. So we made less than we were expecting. And that doesn't mean that our reaction didn't work at all. It just means that it didn't work as well as we would have liked. You know you've really messed up when you make more stuff than you should have. That's a bad sign. That makes your organic chemistry TA really annoyed. Okay, so to calculate percent yield, we just need those 2 things, actual yield, theoretical yield, and it's just a percentage. So this is how we communicate the difference between what we got and what we should have gotten. So you take your actual yield, so how much stuff you got out of your reaction, and you divide it by how much stuff you think you ought to have gotten out of your reaction, so your theoretical yield. And then because it's a percentage, we multiply by 100. If the actual yield equals the theoretical yield, then we say the reaction has gone to completion and it's 100% efficient. And that's a good thing when that happens. So if you have a lower percent yield, that's usually bad. So you want a high percent yield if you have a really effective reaction. Okay, so if we want to calculate percent yield, like I mentioned before, we have to first think about how much stuff we could make. So we're going to look at the same reaction, but we're going to use some different numbers than we looked at earlier. So methane reacts with oxygen to make carbon dioxide and water. This is a basic combustion reaction. 5 grams of methane reacts with 5 grams of water to produce 2.48 grams of carbon dioxide and 2.01 grams of water. So if we want to calculate the percent yield, what we need to do is figure out our limiting reactant. So how much CO2 and H2O can we actually make based on our reactants? Which one do we run out of first? And then once we know that, we can calculate our percent yield. So first things first, find this theoretical yield. Our plan is to identify the limiting reactant and calculate how much product can be made. So if we look at this for methane, 5 grams of methane, and then the molar mass of methane, mole to mole ratio, 1 to 2, and then moles of water, the molar mass of water. So we can make 11.23 grams of water. And then we're going to do the same thing for oxygen. 5 grams of oxygen, molar mass of oxygen, mole-mole ratio, molar mass of water, and we can get 2.82 grams of water from the oxygen. So that's a big difference, 11 grams versus almost 3 grams. So this means that oxygen is definitely our limiting reactant in this instance. We don't need to check for carbon dioxide separately, because if something's the limiting reactant for one product, it's going to be the limiting reactant for the other product as well. Okay, so we know now that 2.82 grams of water can be made. Now we got to check our CO2. And we know oxygen's our limiting reactant, so I don't even need to figure out how much CO2 methane can make, because I know that oxygen is the limiting reactant. So I'm just going to look from 5 grams of oxygen to how much CO2 can be made. Oh, this says, whoops, H2O, it should say CO2. I'll go back and fix that. But we get 3.44 grams of CO2 can be made. So we have both of our products now, our theoretical yields. Theoretically, we should have 2.82 grams of water and 3.44 grams of carbon dioxide. So the next step is to calculate the percent yield of the reaction using the theoretical yield and the actual yield, which is given up here in the problem. So the percent yield for carbon dioxide is 2.54 grams divided by the actual yield of carbon dioxide, which is 3.44 grams, times 100 gives us 71.28. If we do the same thing for water, we can do 2.01 divided by 2.82 times 100 gives us that the percent yield is 71.28. This makes sense because if a reaction doesn't work all the way, typically you will have the same percent yield for all the products, unless there's something hinky going on that is outside of the chemical reaction itself. Okay, so that's how you find a percent yield, but how do you use a percent yield? So in this example, we have solid aluminum reacting with oxygen to make aluminum oxide. And this is 95% efficient. So the percent yield is often written in parentheses to the right of an equation to show the efficiency of the equation. So this question is asking us, if 40 grams of aluminum react with 45 liters of oxygen gas, how many grams of aluminum oxide are formed? Oh, excuse me, guys. If 85 grams of aluminum oxide are produced, how much O2 reacted? This is a two-part problem. Let's focus on part A first. So part A, we're going forward. So we're saying 40 grams reacts with 45 liters of oxygen. So right away, that looks like a limiting reactant question to me because it gives me 2 amounts of reactant and I need to figure out how much product I can truly make. So identify the limiting reactant and determine how much product can be made based on the percent yield. That is part 1 of my plan. So I'm going to start with the aluminum first. 40 grams of aluminum, molar mass of aluminum is 27. Use our mole-to-mole ratio from our balanced chemical equation. Use the molar mass of aluminum oxide. I get 75.56 grams of aluminum oxide. Now that's how much I could theoretically make. But I know that my reaction is only 95% efficient. So I'm going to take my theoretical yield and multiply it by my percentage, turned into a decimal. And that's going to give me my actual yield of aluminum oxide from this process. So I make 71.78 grams of aluminum oxide from the 40 grams of aluminum. Next, we'll do the same thing for oxygen. We're going to use our 22.4 because that is the conversion from liters to moles for a gas at STP. So we're going to go moles of oxygen to moles of aluminum oxide and use the molar mass of aluminum oxide to get the mass. So this gave us 136.61 grams of aluminum oxide. Again, that's my theoretical yield. I have to account for my efficiency of 95%, so I multiply by 0.95, and that gets me 129.78 grams of aluminum oxide. So now I can confidently say that aluminum is my limiting reactant, and I can only make 71.78 grams of aluminum oxide in this reaction. Part B says if we made 85 grams of aluminum oxide, how much O2 would we need to use? So now, instead of going forward from reactants to products, we're going backwards from products to reactants. And so this is going to change things up a little bit. We need to use the actual yield given by the problem, 85 grams, and the percent yield, 95%, to find the theoretical yield before finding the amount of reactant. So here, since we're going from our actual yield to our theoretical yield, we're going to divide by 0.95. So if you're going forward with the arrow in a reaction, you multiply by the percent yield. If you're going backwards from products to reactants, you divide by the percent yield. Okay. So here we have 89.47 calculated from above. Use molar mass, mole-to-mole ratio, moles to liters of gas. We find that we would actually use 29.47, that should say liters, so many typos, sorry guys, liters of oxygen. Okay. So I have here some practice problems for you that you should work through. There are some answers, and I'm going to make a really short next video to talk to you guys about multi-step reactions. And then that'll really be it for our stoichiometry unit. So be looking for a review on stoichiometry the second half of this week. Thanks, guys.